So, you can cancel out the error even if the frequency of the malfunction is very high. This is the point. If you are able to work with Ln equal to Ln. Okay? Good, very good. Because in a way, if you change the wavelength of the source, you are working in the same condition that we have seen when we have evaluated the noise equivalent displacement related to the phase noise. Because recall, since the laser bandwidth is not zero, what does it mean? That the instantaneous frequency changes. And what does it mean? That you have a variation in the interferometric phase. More or less, this is exactly the same thing to say, okay, I have a bandwidth in frequency, of course I have a bandwidth in lambda, in wavelength. So more or less this is the same that happens. And as you have seen before, you can cancel out the contribution if you use a balanced interferometer. An interferometer in which Lm is equal to Lr. Okay? Question, how you can do a measurement in this condition? So now, let's suppose, so don't look at this image, but let's suppose this is not related to the exercise, this is an extra part, that you are working with Lm equal to Lr, okay? You are in this context. Now, if this distance changes because of movement of the target, of the loudspeaker, this condition is not satisfied anymore, okay? So how could you really believe that it's possible to work always in this condition, even if the loudspeaker or the target is moving? You must do something more, okay? You must use a, let's call it feedback circuit. Then, what does this circuit do? This circuit senses what? The photo-detected current or the photo-detected voltage. This is not really important. So let's suppose that I'm using the photo-detected voltage. So, in a way, I know this feedback circuit knows how much the target is moving. Okay? And so what does it do? This drives, for example, a piezoceramic actuator that is mounted on the reference mirror. And what does it do? If I have a variation of this one of Lm, then I move also the reference mirror. Okay? This is the idea. If the feedback is good, is correct, then I will read the movement of the target by reading the error signal. So let's suppose that here I have, it is usually called an error signal, and this is in particular proportional to the displacement of the loudspeaker. Okay? So this is what you do in reality, to try to always work in a balanced condition. Okay? Good. Okay, last question of the exercise, or let's say of the review of this exercise. Now, I want to use this instrument to measure vibrations that are very low vibration, so that, let's say, the amplitude of the vibration is, let's say, S0 is now between 1 nanometer and 100 nanometer. The maximum displacement is, of course, less or lower than lambda 0/2. Okay? So I need to change something. in my approach. For example, one of the possible solutions is to try to work at the alpha fringe working point. Okay? This is the idea. So, if this is true, I know that I can perform analog measurement of the signia, not digital. This is an important point. Probably I already said this, but it is important to repeat. And what is the real limit? We have two possible limits. We have to deal with noise equivalent displacement, and in particular you have two contributions. You have an head that is related to the phase, okay, and you have an head that is related to the quantum noise that is generated by the fact that you detect a photodetected current, okay. So let's call it net Q, okay? So, the net related to the phase, I never recall this, to be honest, is always given by Lm minus Lr, and this is multiplied by the ratio of the laser line width in terms of frequency, so we can say df of the laser, divided by the frequency, the central frequency of the laser. Okay? Whereas the net related to the quantum noise is given by lambda 0 okay, lambda 0 divided by 2 pi v multiplied by the square value of Q by B mean divided by 2 is 0. Okay? Q is the electron charge. Okay? And then you can use the bandwidth that you have just evaluated. You can work with a minimum value or another value. The important thing is that to say what is this bandwidth. Okay? And E0 is the mean value of the photodetected current. So E0 is E0 is given by what? By sigma multiplied by P1 plus P2. Recall this. Okay? And in particular, I don't know if I have evaluated this because I have not the... Sorry? No, V is the fringes visibility. I was coming to this term, okay? Because remember that if you want to use the more general form of the interferometric signal, you have to use fringes visibility, okay? In this particular case, what is the value of the fringes visibility? You can evaluate with this quantity if you go back to the discussion that we have done on the power, on the optical power. Because as I said, of course, the fringes visibility have a particular relation with the that use the coherence length of the source and compare the coherence length with the total difference Lm minus Lr. But if we are in a condition in which the difference between these two arms is much lower than the coherence length, then the fringes visibility is more or less exactly the same as the modulation index of the interferometric signal. So in a way, this is given by two terms. You can evaluate this as 2 multiplied by the square product of P1 by P2, P1 plus P2. Okay? This should be equal also, try to check this, to just a moment. Okay, by P1, so P max. So P max minus P min divided by P max plus P min. These two quantities should be equal. Okay. So once that you have all of the term, the mean value of the photodetected current and the value of the fringes visibility, you can evaluate you can do the calculation. Try to check this because it's probably wrong. I have used, or let me check. Okay, so I did not give to you the result because I have probably used 1 for the fringes visibility, so the calculation is wrong, okay? What is important to say is that in this condition, even if the fringes visibility value is 1, or it is wrong, the limit related to the quantum noise is always lower, okay, than the limit that is related to the phase noise.
Sorry, I think that there is a factor 2 in
there, so
the formula that is, I think, yeah, because...
I think so. I think so.
No.
Well, if you have a full modulation, of course, P min is 0. And so you have 1 when you have P max divided by P max. So I believe that it should be good.
Okay.
It should be good. I will check that. Okay. So, more or less, you get, just to give you the idea, femtometer of possible resolution, okay, or of possible limit. So this is a huge result, even because you are using a bandwidth that is more or less of some kilohertz, okay? You are seeing a number of fringes that is 17, well, not too bad. I mean, the dynamic of the experiment is a bit high, okay? And you can measure displacement of 1 nanometer with this resolution. So this is very, very incredible in a way. The only thing that is important is always to try to work in a condition in which this is true. Okay? In order to cancel out the contribution of, or the noise equivalent displacement that is related to the phase, or to the laser line width. Okay? Okay. we can conceal these, we can go on. We can go on with another exercise, okay? So, more or less, we have the same situation. We have again a Murchison interferometer. The different thing in this exercise is that the target is not a loudspeaker, but it moves with a particular signal. So we have that L1 is equal to is equal to 1 meter. Then we have that L2 is equal to 0.2 meter. Then you have LR is equal to 0.2 meter, and LM is equal to LM0, let's say, is equal to 0.2 meter. And then what you have? You have that you have a time varying component of the measuring arm. It is given by this relation. So you have a DLT, okay? I have to find 10 time. Okay. The scale here is, the time is in millisecond, and the variation in length is measured in micrometer, okay? Maximum displacement is of 0.5 micrometer. Then in the first millisecond, the measuring arm is at rest. Then you start to move away from the instrument, and then you have, so this is 1, this is 4, a linear increase of distance from LM0 to LM0 plus 0.5 micrometer. Then again, another 3 milliseconds, the target goes back toward the instrument. Then here in 1 millisecond it goes to 0.2 micrometer. And then in the last 2 milliseconds it remains still. Okay? So this is 10, this is 9, and this is 8, and this is 7. Okay, this is what happened. We have a bit of change, because now the line width, that is the important thing to solve the first part of the exercise, is not 1500, but it is 1800 nanometer. Okay? 1800 nanometer. And the exercise says that you are using a resolution equal to lambda 0 divided by 2. Okay? I'm late? Oh, no. Now the point is, try to give a picture of what happened onto the photodetected current. Okay? This is the idea. Using, let's say, a synchronized graph. Okay? Now I don't want to be. I go a bit fast because what is the starting condition? Okay, the starting condition is a condition in which we have that the reference path is exactly equal to the measuring one. Okay, because this 0.2 is equal. Okay, now, in your opinion, what is the starting value of the photodetected current? In this case, you have that the reflectivity of the reference and of the let's conceal the loudspeaker. Here we have a mirror and the reflectivity is 100%. Okay? The beam splitter is still a 50-50 beam splitter, but if these two reflectivities are equal, this means that the photodetected current is fully modulated, or the fringe's visibility is 1. Okay? So now, in this condition, you start from the maximum, from the minimum, for the lowest possible value of the photodetected current, or a value between. Since we have LR equal to LM, we have a signal that is proportional to the cosine of 0. So we have the maximum value. So we will start from, if this is, okay, let's suppose that this is the mean value, okay, we will start at time t equal to 0 of a quantity that is 2 is 0. The power emitted by the laser is still 10 milliwatts. Okay, and the sensitivity of the photodetector is still 0.5 ampere over watt. Okay, this is used to evaluate the 0. But at the moment, it's important to understand what it will be, the interferometric signal. Because we remain still in the first millisecond. So what does it mean? That the interferometric phase does not change, and so we will have a maximum value for the photodetected current. Okay? Then what we have in these 3 milliseconds? The measuring arm changes of a quantity that is equal to 0.5 micrometer. Okay? The resolution in this case is, since the wavelength is 800 nanometer, the resolution is 400 nanometer. Okay? So what does it mean? That when we will be here, 0.4 micrometer, what we will see on the photodetected current? Remember that if the measuring target moves of a quantity that is equal to lambda over 2, in this case 400 nanometer, we see a full period in the interferometric phase. So we have something that is more or less like this. Okay? And the minimum value is 0 because of the full modulation. Okay, this is not exactly a cosine function, but okay. Then what you do, or well, what you will see on the photodetected current if you go from 0.4 to 0.5 nanometer. Sorry?
It's like saturated, so it should like stay.
No, this is not correct. Of course, you are moving of a quantity that is not equal to the resolution. Okay, so you will not see, let's say, a period of variation or a full variation of the photodetected current. But 100 nanometer, that is the difference between 0.5 and 0.4, is 1/4, okay, of this quantity. So what does it mean? It means that if you move of a quantity that is equal to 400 nanometer, you see a full 2 pi period of development in the interferometric phase. If you move just 1/4 of this quantity in the interferometric phase, you will see a variation of pi over 2, or a quarter of the period. So you will finish here. Okay. Okay. Then what happens if you go back toward the instrument? You will continue, let's say, in this way, or here you will have a discontinuity in the signal. Yes, that's correct. You will have a discontinuity, and in particular, you have something like this. You go back to the maximum, and then you go back here, okay? Then you move in a 1 millisecond, again far away from the instrument, and now the displacement is of 200 nanometers. So if 400 nanometers correspond to a full period, 100 nanometer correspond to a quarter of the period, 200 nanometer correspond to half of the period, and so you go to 0. And then once you are here, since the target stopped to move, the photodetected current will remain at 0. Okay? Okay. Last thing, last thing. Let's try to evaluate what is the value of E0, or of the mean value of the mean current. What I have written before is, of course, always true. So that E0 is always given by sigma multiplied by P1 plus P2. Since in this case reflectivity of the measuring and reference mirror is the same, and it is 100%, we have also that P1 is equal to P2 and is in particular equal to P0 over 4. Okay? So it means that E0 is equal to sigma, that is 0.5, or 1 over 2, multiplied by, for example, 2 is 0 divided by 4, and this is equal to 2.5 milliamp. Yes. 2.5 milliamp. Okay? Okay, we are finished.